The most surprising thing about this discovery was just how bright the object appeared. At first glance, that brightness made researchers doubt the possibility that it could be very far away. It just seemed too luminous to belong to the early universe. But with better data and detailed spectroscopy, it became clear. This yellow blob in the image wasn't just any galaxy. It was, in fact, the most distant galaxy ever seen. That finding alone is remarkable, but it's only the beginning of what might be one of the most significant scientific upheavals in recent memory. Some of the most respected voices in astrophysics, including Nobel Prize winners, are now suggesting that the new data from NASA's James Webb Space Telescope is challenging the very foundation of our understanding of the universe's birth and evolution. Designed to look deeper into cosmic history than any telescope before it, JWST has returned with results that defy expectations. Within months of its deployment, it detected galaxies so enormous, so bright, and so developed that their existence seems to contradict everything we thought we knew about how the universe formed. Among those speaking out is Adam Rees, a Nobel laureate recognized for discovering the universe's accelerating expansion. He now says there's a very real and thrilling possibility that our understanding of the universe has been fundamentally flawed. The telescope's observations from the era known as the Cosmic Dawn are forcing scientists to revisit decades-old theories. JWST's nightmare data, as some call it, is anything but subtle. To understand why this is so groundbreaking, we have to look at what exactly JWST found. The telescope captured light from galaxies that formed just 300 million years after the Big Bang, a blink in cosmic terms. But these galaxies were not the chaotic, amorphous clouds scientists expected. Instead, they were large, well-structured, and bursting with stars. According to our existing models, there simply wasn't enough time for such complex structures to form. One such galaxy, known by the technical designation JADAS GS Z140, was observed at a redshift of 14.3. This means we are seeing it as it existed only about 290 million years after the Big Bang. Far from being a faint speck, it's a blazing star-forming system, more than 1,600 light-years across. Scientists were stunned. One even said it was astonishing that such a galaxy could exist so early in cosmic history. And it's not just one anomaly. JWST has revealed thousands of early galaxies that defy expectations. Many of them are far too advanced, displaying characteristics like spiral arms and bar-like structures, features we associate with much older, stable galaxies. Surprisingly, between 50 to 80% of these early galaxies are flat and elongated, resembling surfboards or pool noodles, rather than the round, shapeless blobs predicted by our models. These shapes imply a level of organization that shouldn't be possible so soon after the universe began. To put it in perspective, it's as if scientists expected to find simple microbes in Earth's earliest oceans, but instead discovered fully developed mammals. The disconnect between predictions and reality is staggering. This has prompted a flurry of theories, and some researchers are openly wondering if we've misunderstood the cosmos altogether. The implications go beyond a few unusual galaxies. They strike at the heart of the Lambda CDM model, the standard model of cosmology that has guided our understanding for decades. According to this model, a universe dominated by cold, dark matter should have built structure slowly, starting with tiny proto-galaxies that merged over billions of years. But JWST is showing us a young universe that looks far too mature, brimming with massive galaxies that rival our own Milky Way, despite existing when the universe was just a few percent of its current age. One astronomer, Alison Kirkpatrick from the University of Kansas, summed it up starkly. Everything's too big. It's too big, too soon. This isn't a small oversight. It's a fundamental contradiction between theory and observation that has scientists questioning the foundations of their field. The Atlantic even reported that JWST's data has launched researchers into a new reality where their theories no longer apply. Some initially wondered if the telescope's instruments were malfunctioning, but the calibrations checked out. The data was solid. What it revealed was nothing short of a crisis in cosmology, and the reactions from Nobel-winning scientists have been equally extraordinary. Dr. John Mather, who won the 2006 Nobel Prize for his work measuring the cosmic microwave background, and now leads JWST's science team, admitted the galaxies weren't what anyone expected. They're too bright, too powerful, and far more numerous than models predicted. Mather's admission carries huge weight. After all, he helped design the very telescope delivering these paradigm-shifting results. Adam Rees, leading a JWST program to address the Hubble tension, a discrepancy in measurements of the universe's expansion rate, was also hoping for clarity. Instead, JWST's precision only confirmed the problem, ruling out measurement error. Rees responded by saying that the only remaining possibility might be that we've misunderstood the universe itself. He told Live Science that the conflict in data makes us question whether we truly understand the universe's composition or its underlying physics. Another fascinating voice in this discussion is Sir Roger Penrose, the legendary physicist and 2020 Nobel laureate. He interprets JWST's findings through the lens of his conformal cyclic cosmology theory, which suggests that the Big Bang wasn't the beginning, but merely one phase in an eternal series of cosmic cycles. According to Penrose, these advanced early galaxies might actually be remnants from a previous universe, poking through into our own. While his theory is speculative and not widely accepted, it illustrates just how much these discoveries are expanding the boundaries of scientific thinking, even among its most accomplished figures. What all these reactions share is a recognition that JWST isn't just filling in gaps in our understanding. It's challenging the very structure of the picture itself. Rees described it not as a reason for despair, but as an exciting opportunity to uncover new layers of truth. But the surprises didn't stop there. The Hubble tension, the discrepancy in the universe's expansion rate, has grown even more troubling. For years, two methods have yielded different results. When astronomers measure the expansion locally using stars and supernovae, they get about 73 km per second per megaparsec. When using data from the cosmic microwave background, they get about 67. This 9% gap may seem small, but in precision science, it's huge. Too large to dismiss as mere error. WST was supposed to help resolve this mystery by observing standard candles like Cepheid variables with greater clarity than ever before. It aimed to refine our distance measurements. But instead of bringing convergence, JWST's improved data has made the disagreement worse. It confirmed the higher local rate, making it even harder to reconcile with early universe measurements. Rees acknowledged that this result only deepens the mystery and may require new physics to explain. Some theories now suggest dark energy might not be a static force but something more dynamic, possibly changing over time or interacting with matter in unexpected ways. As one science outlet put it, JWST has broken cosmology, a dramatic headline, but it captures the sense that something fundamental isn't adding up. Adding to the intrigue, new research has proposed a possible reinterpretation of JWST's data. A team led by Stephen Finkelstein took a second look at some of the most massive early galaxies and discovered something important. Many of these bright objects were likely being distorted by the presence of active supermassive black holes. These black holes, feeding on nearby material, emit vast amounts of energy and can make their host galaxies appear far brighter and more massive than they really are. This realization, essentially a cosmic illusion, helped resolve a major discrepancy. Once the intense light from these feeding black holes was subtracted, the inferred mass of several galaxies fell into more expected ranges. But even this doesn't solve everything. It only shifts the focus. Because if black holes were already that massive and active so soon after the Big Bang, we're left with a new puzzle. How did they grow so fast? Even after accounting for these deceptive black holes, JWST continues to find more early galaxies than models predicted. This has scientists rethinking core assumptions about the rate of star formation, the behavior of dark matter, and the effectiveness of feedback from early stars and black holes. Some are even considering new physics, perhaps unknown properties, of dark matter or modifications to gravity itself. Despite the shock these discoveries have caused, no credible scientist is throwing out the Big Bang theory. What's happening now is science working as it should, confronting unexpected results, refining models, and expanding the frontier of understanding. Rather than discarding our entire cosmological framework, researchers are considering targeted revisions. Some suggest the early universe might have converted gas into stars far more efficiently than we assumed. Others are re-evaluating the initial mass function, which governs the types of stars that form. If the first stars were typically much larger and brighter, that alone could account for the intense luminosity we're seeing. There are also more exotic proposals, such as early dark energy, a theoretical force that may have given the young universe a temporary boost in expansion before fading away.